there are ways to make the theory renormalizable. And the simplest example is this theory, which is called higher derivative quantum gravity. What is this? It is the Hilbert term with a cosmological constant. Let me put a parameter zeta in front of r, and then you just add the two quadratic terms. This theory is renormalizable. So what's different with respect to the previous theory? The previous theory, you expand perturbatively around this, and eventually you generate those as corrections, which means that those parameters are perturbative. They are small. And actually, those quadratic terms don't even matter because you can reabsorb them into redefinitions of the metric tensor. Here, instead, you expand perturbatively around the entire thing, which means that alpha and beta are not small. Are of order 1. They are dimensionless, actually, so they're really of order 1. And that changes the theory completely, because if you expand around flat space, ignore the cosmological constant for a moment. It's necessary to have the cosmological constant for a normalization, but flat space is not a solution in the presence of a cosmological constant, but we expand around flat space anyway. So if you expand around flat space, the quadratic part here will contain not just the terms we found, but quadratic terms from here and here, which contain 4 derivatives, because those terms have 4 derivatives, something like that. And again, the coefficients alpha and beta in front of those are not small, so the propagator that you want to work out is the reciprocal of a polynomial that contains not only p squared, but also p to the 4th, p squared squared. So in the ultraviolet at high energies, for p squared large, this propagator decreases like p squared squared, not p squared. And that's sufficient to make the theory renormalizable. Why? Because now the dominant term in the ultraviolet is this one, not this one. This one is not important in the ultraviolet. And so when we repeat the power counting, we have to determine the dimensions of this term. So here you see alpha has dimension 0, like beta, because they multiply r squared. Zeta, no, in this notation there is the k squared in front. So alpha and beta have, there is one constant is redundant here because I like it. So there is a kappa, there is lambda, zeta, alpha, and beta. So if I want, I can get rid of one of them because I introduce one more. So let's say the dimensions of one of them we can choose to be 0, for example. Let's say that alpha, let us say alpha equal beta equal dimensions of alpha and beta equal 0. Then what are the dimensions of the other things? Dimension of zeta is 2 because, so let's say, then dimension of zeta is 2, and the dimension of the cosmological constant lambda is 4. No, actually, this is too early to say because I want to derive these two things, and I cannot derive the dimension of that, strictly speaking, from here because let's do like this. Let's choose alpha and beta equals 0. Actually, it's better to move it to the next page. And so when we expand around flat space, the quadratic part, the quadratic terms, simplify the k squared because 2 phi's bring 2 k's. So they simplify the k squared. And so this term, which has partial phi is multiplied only by zeta. And these two terms, which have 4 partial derivatives, can be multiplied by alpha or beta. Okay. And then there is a cosmological constant, we don't care. Now the question is, okay, alpha and beta, we have said they are numbers, they have dimension 0. Then what is the dimension of this? It must be 4, but this has 4 derivatives, which means that the dimension of phi is 0 now. So the scalar field has dimension 0. If the scalar field has dimension 0, this has dimension 2, so zeta has dimension 2. Lambda has dimension 4. But what is important is that kappa has dimension 0, because kappa appears here. Now phi mu nu has dimension 0, kappa phi has to have dimension 0 because it has to be the same dimension as the one of eta mu. So now that phi has dimension 0, kappa has dimension 0, the theory does not contain any coupling of negative dimensions. So necessarily it is renormalizable. No parameter of negative dimension and that means that you cannot even construct a counter term like that, because you should write in front something that has dimension -2, and every parameter must appear polynomially. But alpha and beta. In the counter terms. But alpha and beta. Why? Because check the propagator. The p to the 4th terms have coefficients alpha. The p squared terms have coefficient zeta, alpha or beta. And then you repeat the argument the other time. If you differentiate a propagator with respect to zeta, you lower the behavior at infinity. Okay, so let's do it. Let's also check this, add a cosmological constant as dimension 4. This goes like 1 over p squared squared. So if you, let's say that this is p. If you differentiate p with respect to zeta, how does that behave at infinity? If you differentiate that with respect to zeta, you square the denominator, and in the numerator you have the differentiation of the denominator with respect to zeta, so you have that. Well, you can compute it exactly. So that goes like 1 over p squared cube at infinity. And therefore, after a few derivatives, you will have something convergent. If you differentiate with respect to lambda, even better, because you get the same without p squared in the numerator. But if you differentiate with respect to alpha or beta, you don't get any improvement. And that means that if something is divergent, it remains divergent, no matter how many times you differentiate with respect to alpha and beta. So the dependence on alpha and beta will not necessarily be polynomial. It can be anything. But that doesn't matter because alpha and beta are numbers, they are dimensionless. The point is that the coefficients, the dependence on the other parameters, those that have positive dimension, can only be polynomial. So they cannot appear in the denominator. They cannot appear in the denominator, and they cannot generate something of negative dimension. K doesn't matter because it's dimensionless. So you cannot construct. You could say, oh, but there is phi now that has dimension 0. So a priori I can construct arbitrary functions of phi. But gravity, not quantum, or classical gravity, does not allow you to build arbitrary function of phi. It's not a scalar field. You have to have covariant objects, scalars, in the action. The action must be a scalar. So if it is local in derivatives, even if phi has dimension 0, you just have few invariants that you can build with those constants that are local and depend on the parameters polynomially. And they are the same here. One, r mu squared and r squared, which will be multiplied by functions of alpha, beta, zeta, and lambda, and kappa, which is redundant actually. One of them is redundant, but it's useful because this is like h bar, so it's better to have it. And this theory is strictly renormalizable because its coupling kappa has dimension 0. So all divergent paths you can compute from this one. So this theory is strictly renormalizable. All the divergent paths are the same type. Said to be strictly renormalizable when there are no couplings of dimensions of negative dimension, but at least one has 0 dimension. Kappa has 0 dimension. Are there ways to make the theory more renormalizable? Yes, if you want, you can make it even more renormalizable. By adding more quadratic terms. So one thing you can do is to add the terms that have dimension 6 and are quadratic. Again, there are only 2. In the quadratic sector, there are others. Let's say cubic terms. So theories like these are super renormalizable. That means that the parameters have all strictly positive dimension. Kappa in particular has strictly positive dimension. Why is that? Because now the dominant term in the ultraviolet, dominant quadratic terms, are given by those. So you have phi, let's say delta, phi. How many derivatives? There are 2 derivatives in R mu nu, 2 derivatives in R mu nu, and a box. There are 6 derivatives. So you choose now dimensions of delta and gamma equal 0. And then you will have that beta will have to have dimension 2 like alpha, and then zeta will have dimension 4, and lambda will have dimension 6. But the important point are the dimensions of phi and kappa. So if delta has dimension 0 and the object here needs to have dimension 4, here we have 6, phi must have dimension -1. And if phi has dimension -1, kappa phi must have dimension 0, and so kappa must have dimension 1. And since 1 over kappa squared multiplies the action overall, this is like h bar. So again, at L loop, we have the counter terms at L loops carry an extra factor k squared to the L, which has dimension 2L. So at 2 loops it's dimension 2. At 3 loops, at 1 loop has dimension 2. Then 4, 6. Well, you cannot construct many invariants with this because so at 1 loop you have a k squared which has dimension 2, and now you have to, yes, an extra factor, extra with respect to 1 over k squared, so that means you have nothing. So at 1 loop you have again r squared plus r mu nu squared plus r plus lambda. But at 2 loops you have a k squared in front, and that has dimension 2. So in total you need to have dimension 4. So you just remain with that. At 3 loops you have k squared squared, k to the 4th, and that means that you can only multiply by the cosmological term. At the 4 loops you don't have any divergence. So in a supernormalizable theory, the number of divergent terms quickly disappears after a certain order of the perturbative expansion. However, all these theories have a problem. These theories have a serious problem with unitarity. And here I should add, if quantized in the ordinary way. Because the solution is to quantize not in the ordinary way. Why are they not unitary? Well, because we said that the propagator has this form here. So propagator is something like, well, there is a p squared squared plus p squared. So let me write it. This is a propagator with the denominator, which is a polynomial of p squared of degree 4. Let me call that coefficient, second coefficient, minus m squared, and the other one equal to 1. Well, it's a mass, so let's call it like that. This we can decompose into 1 over p squared, 1 by p squared minus m squared. So if we take the difference and actually take this thing and divide it by m squared, yes. We should actually put a minus here so that at low energies, minus m squared. Why that normalization? Because that is this difference. So when the mass goes to infinity, which means at low energies, when p squared here is negligible with respect to m squared, you get 1 over p squared. So we start quantum gravity at low energies is 1 over p squared when the mass goes to infinity. But in this theory, due to that, you see that the propagator has two poles, and one has a positive residue, and that's fine. But the other one has a negative residue, and that violates unitarity. So if we repeat that argument with this kind of process, where was it? So this was IT, and that was negative definite, okay? But now it's the sum of two delta, difference actually of two delta functions. Let's copy this. Two real part is minus pi It is the difference of two delta functions, the one that's okay with the correct sign, but the other one is not okay. This is not negative definite. Cannot be minus t dagger t, because it's the difference of two delta functions. And so this thing is a ghost. Not a Faddeev-Popov ghost, one of those that are introduced to make the gauge theories work and compensate something else. So they are there for a reason. This is a serious problem that doesn't compensate anything. It has a different mass, so it doesn't even subtract the other thing. So this is the problem of higher derivative theories. One can ask, is there a problem at the classical level? Yes, these theories have problems also at the classical level. Higher derivative theories. The problems are not called ghosts, they are called in a different way, but they are there. So instead of having a Lagrangian that depends only on Q and Q dot, now you have a Lagrangian that depends on higher derivatives. Let's see. And that means that you do not have a Cauchy problem, because instead of giving positions and velocities, you need initial conditions. You need to give positions, velocities, accelerations, so on and so forth. You could say, but I can add variables. I can always get a L of QQ dot, some psi dot, zeta dot. So the Lagrangian that depends only on positions and velocities if you enlarge the set of positions. But you can easily see that if you do that, starting from a higher derivative theory, the Hamiltonian of the new action will not, the new Lagrangians will not be bounded from below. And so you have an instability. It means that you cannot have an evolution towards a state of equilibrium with minimum energy, because there is no minimum energy. You will have a totally unstable system or universe. However, at the classical level, there is a way to turn this around. And then we will see that it will not be straightforward, but there is a way to do the analog thing in quantum gravity. So let's consider a case that you might have heard from classical electrodynamics. You know that a charged particle that's accelerated radiates, and so it slows down because there is a sort of friction. But that's not a friction. It can be described by an equation which has higher derivatives, which is not F equal ma, but ma minus some thing that contains the derivative of the acceleration equals the external force. This is an effective equation, but it doesn't matter here. It cannot even be derived by Lagrangian because it's a sort of friction. But what matters is the argument we are making. So let's assume we have something of this type. This thing has, by the way, in classical electrodynamics, this is it. There's a constant positive. This theory has runaway solutions even without external forces. Which means, let's assume there is no external force. Then, if the particle is here at rest, it should stay here at rest. But this is not true, because you have a solution that is this thing. So you have a solution, so does not imply that, because you have a solution that is A equals e to the t divided by tau times a constant. And this is x dot dot. So when from this you derive v x dot of t, you will have something like that. Yes, the integral. And if you want, x of t is equal to let me call that the initial velocity. And so you will have c times tau squared t over tau minus 1 plus t, let's check because so if I take the derivative here, I have v0 c tau. If I take the derivative of this, so c tau is that, there is a minus. And if I take the derivative of that, I take that. Yeah, should be correct. So I can impose, see I have a solution with three constants. I can impose x0 equals 0. Yeah. If I want to say that the particle is at rest in the origin, then I have this kind of solution. But t equals 0 is at rest in the origin. But, so this goes away. But for non-zero t, it goes exponentially to infinity. Okay, so this is the runaway solutions are the classical a-classical analog of the ghosts. There are other things but typically these are extra solutions that you do not want. Well, there is a way to get rid of these extra solutions, but you pay a price. And the price you pay is that you violate microcausality. Physically speaking, causality at very small distances is not a very strong principle. And in quantum field theory, causality itself is not a very strong principle. So unitarity instead is a very strong principle. Because if you have something with negative residues, it means that you are violating the law. It's like having negative probabilities or like having a negative number of particles. Because the residue is the number of particles. It's the z factor, which is number of particles in your flux. It's like having a negative number of particles, or particles with negative norms, of negative probabilities. This is really bad. But if you violate causality, we'll see it's not really a big deal. And then you will see that the same price can be paid in quantum field theory to make the theory both unitary and renormalizable. So the theory, the higher derivative theory that we saw is renormalizable but not unitary because of the presence of these ghosts. So the ghosts solve the problem of renormalizability but create a bigger problem, which is unitarity. So it's better to stay to the Hilbert action with infinitely many terms, which is not renormalizable, but at least it's predictive, it is unitary.